Hello, everyone. I'm Jiahui. In this video, I'm going to present our work, Multi-Party Private Set Intersection Cardinality and its Applications. This is a joint work with Nichu and Avishai Yanai. And this is the content for the presentation today. So private set intersection is a well-studied problem in the context of multi-party computation. This figure shows a two-party case where the receiver and sender each have private input set X and Y. And the receiver should learn the intersection of these two sets, while both of them learn nothing else apart from the final output. In this case, the result is P and S. And private set intersection cardinality is something different. Instead of learning the actual intersection elements, P and S, in the previous case, here we only want to learn the size of the intersection set. In this case, it's 2. For our work, we consider the PSICA problem in the multi-party setting. So the PSICA have many applications. The first one is called dot product. So suppose you have two binary vector v1 and v2. We can convert these two vectors into two sets by recording the non-zero elements position in the original vectors, and then compute the PSICA functionality on these two sets will give you the value 2, which is the product of the original vectors. Another application is called heat map detection. So consider a scenario where the Department of Health and Human Service want to learn the area where there's a higher chance of getting affected with the disease without knowing the travel route infected individuals. So basically, the HHS have a data set which is a vector X representing a positive patient of a specific disease, such as COVID-19, where in this vector 1 means the specific person have been tested positive, and 0 means negative. For the network operator's input, which represents a location, such as a building, it also maintains the same length of binary vector, where 1 means the user have been visited this location and 0 otherwise. So the dot product for the red vector with any blue vector gives you the number of positive visitors to that location. By aggregating all the result for each blue vector, you can construct a heat map look like this. So instead of doing that by aggregation of personal travel route for infected people, you can do it in the privacy preserving way as I just introduced. So here are some previous work for PSICA protocol. The first work is KS05, which is the polynomial-based method with homomorphic encryption. So in their design, each party represents the set as an encrypted polynomial, and then they aggregate the polynomial to compute a global one, and then they evaluate their own private input on this global polynomial under the additive homomorphic encryption. The decryption of the number of zeros will give the number of intersection cardinality. The inefficiency is from the homomorphic encryption. MRR20 is one work requiring 3 non-colluding server compute the PSICA functionality in a secret sharing way, and it has a large communication cost. The state-of-art multi-party PSICA comes from the work of CDG21 by conducting the multi-party circuit PSI, where the party align the data using the cuckoo and simple hashing technique, and the leader conduct the circuit PSI with each party, and then from the share received of these pairized invocation, cardinality can be computed from the MPC technique, but that also introduced heavy computation and communication cost. Before we introduce our design, here's some preliminaries. The first one is called oblivious pseudo-random function, OPRF, which is a two-party protocol where the receiver have a query X and the sender have a PRF key K. And the receiver will learn the PRF value of the query X with respect to the key K, while the sender learns nothing. So oblivious programmable pseudorandom function OPPRF gives an advanced feature to the OPRF. So here the sender can additionally have a set of key value pairs, in this case yi and vi. So instead of directly learning the evaluation for the PRF of query x, the receiver will learn vi if the query x equal to any of the key yi in the sender set. And this key value store, which is a technique, can realize the functionality of OPPRF by encoding the key value pair into a data structure, which leaks no information for the original input, while can allow other parties do the decoding given the key. The simplest construction for OKVS is a random polynomial. The unconditional zero sharing is a multi-party protocol where all the parties agree on the sharing function S, and each party PI learns a key KI. So for a input value X, the party PI can compute a random share for X as SKIX. If this X is the same for all the parties, then the share will be XOR to 0. So based on what I just introduced, we propose two new building blocks, the server aiding OPRF and server aiding OPPRF. So for server aiding OPRF, we consider a double key PRF where the FKX is equal to the FK2 and FK1X. So in this case, the sender have the key, which is a pair K1 and K2. The sender send the K1 to the receiver and the send K2 to server. And then receiver can compute the first layer of the PRF, which is FK1Y, and send it to the server. And server can return back with the other layer of PRF. And we realize this functionality can be easily extended to a server aiding two-party PSICA protocol. So instead of directly sending the PRF evaluation of the receiver set Y, the server send back the permutation of it. And at the same time, the sender can send the PRF value of his set X. And then the receiver can compute the cardinality of these two sets, which is equal to the cardinality of the original input X and Y. We also have something similar for OPPRF in a server aiding setting. So please refer our paper for more details. And now we are ready to introduce our main construction, which is the serverless multi-party PSICA protocol. So the idea is like for a element X belongs to Xn, we want to check whether this X also belongs to all the other parties through P2 to Pn-1. And if yes, then Pn will learn a PRF value of this element with respect to key S. And at the same time, P1 can also compute the PRF value of his input set X using the same key. And then P1 and Pn can invoke the server aiding PSICA protocol to compute the cardinality of these two sets of PRF values, where P2 can play as a server. In the previous mention, the server aiding two-party PSICA protocol requires non-cooling server. So in this case, for multi-party setting, we require the P1, P2, and Pn are not clued as well. So the first step for our main protocol is to invoke the unconditional zero sharing protocol among P2, P3 through Pn. Each party will learn a key Ki, and they can compute the secret share for each of their input values as S. And at the same time, the P1 and P2 agree on the secret key S, and they can compute the PRF value for their own input set, X1 and X2. And then each party compute the value V as the share, where the P2 compute the V as the XOR of the PRF value and the share. So for the next step is to invoke the server aiding OPPRF functionality, where before that, each party agree on the key K and then compute the PRF value of their input over this key K. So for PI, they place as the sender. The key will be the PRF value for the input, and the value will be the V from the previous step. The receiver will be Pn with input of the PRF value of his input, and learns the output WI from this functionality. So ideally, if the query belongs to one of the parties' input set, the WI will be the corresponding share. And then the PN compute the XOR of all the sharing. So ideally, if everybody have an element X, then the corresponding value WJ will be FSX2. And finally, P1 and PN can invoke the PSICA protocol with the helping server P2. So here we show the performance comparison with previous work. To compare with CDG21, we run our protocol in the full party cases with different number of elements in each set. To compare with the MRR20, remember our protocol requires P1, P2, and PN not colluding, which is the same as theirs require 3 non-colluding servers. And both comparison shows we have better running time and communication cost. Thank you so much for your listening. If you have any questions, feel free to ask. Thank you.